So I'm going to start class off today. We're just going over a couple review problems for your quiz tomorrow. Let me know if you have any questions over the video solutions that I showed yesterday. So please email me if you have any questions. Your quiz is tomorrow. So just to practice, go ahead and pause the video, copy down this first example, and answer the question. All right, so hopefully you had some time to look this over. Now here we're using Chebyshev's theorem. We have a mean of 65 and a standard deviation of 4. At least what percentage of values will fall between 50 and 80? Now remember, if we get a k is equal to 2 or k is equal to 3, we really don't have to do that work of 1 minus 1 over k squared. But it never hurts. You can't go wrong if you just always use it. So first we need to find k. And remember, k tells us how many standard deviations away from the mean we are. So we start by taking our max value minus our mean, so 80 minus 65 over our standard deviation of 4. So this is 15 over 4, which is 3.75. So that's definitely not a 2 or a 3 exactly, so we do have to do the 1 minus 1 over k squared. This gives us our proportion or our percentage, so 1 minus 1 over 3.75 squared. And this should give us a 0.928 repeating, so we could round this to 93%. So we would answer the question by saying at least 93% of the values are between 50 and 80. All right, so now let's take a look at the empirical rule. We didn't really use too much of this, but it's still important to know the percentages. So pause the video to copy this down. Look back in your notes at the empirical rule. These are 3 percentages that correspond to 1 standard deviation, 2 and 3 standard deviations away from the mean. All right, so if you were able to look that up, remember 68% of our data will be within 1 standard deviation from the mean. Approximately 95% of our data are going to be within 2 standard deviations from the mean, and then this 99.7% of our data is going to be within 3 standard deviations from the mean. So we're working with this. So this tells us we don't have to do any kind of calculation. This is just telling us that we're within 3 standard deviations of the mean. So we have to find the range in which approximately this percent is going to be between. So if we have a mean of 255 and we go to the right, for every 1 unit we go to the right, we're really adding 22. So I have to go 3 standard deviations to the right, so that's going to be 3 times 22. That's 255 plus 66 should give us 321. And then we say 255 if we go to the left minus 3 times 22. 255 minus 66 should give us 189. Therefore, the range of our values is from 189 to 321. So that's going to hold 99.7% of our data values. All right, so you guys can use formulas on your quiz tomorrow. So go ahead and pause this page and copy all these down on a separate sheet of paper, because that sheet of paper is the only thing you'll be able to use on your quiz tomorrow. In class, I will have these up on the board. So your quiz tomorrow will be 9 problems, 25 points. And like I said, you could use these 6 formulas. Notice I don't have them labeled, so you have to know when to use them. I just want you copying them down as they look. So keep it paused if you still need to write these down. I'm going to move on. Okay, so this is what I just mentioned, 9 problems, 25 points. So we're going to start section 3.3 today, a little bit after the quiz tomorrow, and then continue on Thursday. So section 3.1 looked at measures of central tendency. Section 3.2 looked at measures of variance. Section 3.3 looks at measures of position. So we're going to be looking at standard scores. Now standard scores tie in only with the normal or bell-shaped distribution. So that's what we're going to start to look at. Today we're also going to look at percentiles, but tomorrow a little bit more with percentiles and then deciles and then eventually quartiles. All right, so standard scores are also considered to be a z-score. This represents the number of standard deviations that a data value falls above or below the mean. So it is kind of tied into what we were just doing with Chebyshev's theorem, finding k, but that's all that it's connected to. So here's a formula to find our z-score. And there's some resemblance to what the formula was to find k. Instead of it just being the max value, we just have a single value. We're not looking in between a range. We're just looking to convert an individual value into a z-score. So it's the value minus the mean divided by the standard deviation. Now it's going to look a little different for samples versus population, just because of the symbols here. So when we're calculating that for a sample, it's x minus x bar over s. Population, it's x minus mu over sigma. So what we really do, we convert the mean becomes 0 in a z distribution, and the standard deviation is 1. And then this is how it just sort of ties together as well. If our score is above the mean, we should expect a positive z-score, or vice versa. If our score is equal to the mean, we should expect a z value of 0. And then if our score is less than the mean, we should expect a negative z value. So that's what a negative z-score indicates. So if we were to look, kind of going back to that 255 example, if this was 255, and then for every mark over here, this would be another 22. So then this would be 277. That's one standard deviation to the right. And then we have 299. And then we had our 321. So this would be one standard deviation to the right. This would be two standard deviations to the right. And then three standard deviations to the right. And then we could go to the left as well. Right here we would be at 233. At 211. And then 189. So we have three standard deviations to the left. What a z-score does is this now takes the middle number and puts it at a 0. And then we're simply counting 1, 2, and 3, or a -1, -2, and a -3. So it just turns it into simpler numbers we're used to working with on a coordinate plane as well. But that's the comparison, and that's exactly what we're doing. Now, not every number is going to fall right at one standard deviation or two. We could have something in between. We can have a 1.5 as a standard deviation. We can have a -1.75 as a standard deviation. But this is essentially what we're sort of converting to. All right, so let's take a look at this first example. You can pause the video to copy this down. So it says a student scored 65 on a calculus test that had a mean of 50 and a standard deviation of 10. She scored 30 on a history test with a mean of 25 and a standard deviation of 5. We're going to compare her relative positions of the two tests. So first let's start with calculus. So we're going to take and figure out her z-score. So it's going to be her score is 65 minus the mean, which kind of makes sense. You always want to compare how you do to the average of the class. And then the standard deviation was calculated to be a 10. So this gives us 15 over 10, or a z-score of 1.5. So really she was 1.5 standard deviations above the mean. And then we can go through and do history. So the z-score here is going to be 30 minus 25 over 5, which is 5 over 5, which is 1. So her position for the calculus test was higher. So we would just answer this way. Her relative position, let me write that word out. That's what this is showing. Her relative position for calculus was higher. So if we were to draw the normal distribution here, showing our mean was at 0, her history test was just 1 unit, 1 standard deviation to the right, and then if we had a second one, so this is where her history test fell, her calculus test was right here at 1.5. So her relative position was higher for calculus. Okay, let's go ahead and try another one. Here I'm just giving you the information this way instead of a few sentences. So pause the video, go ahead and find the z-score for each test and state which is higher. So really, because we're dividing by different standard deviations, this is why it's important to go through this. So let's take a look now for test A, or you could pause the video if you still weren't done calculating this. So our z-score for test A, we would take 38 minus 40 and divide that by 5. So we're going to get really a negative 2/5, which is really a negative 0.4. And then for test B, our z-score would be 94 minus 100 over 10. So we're going to get negative 6/10. So now because we're on the negative side, this just means, obviously, look, both scores were below the mean, so it makes sense that we were going to get this negative value. So test A has the higher z-score. All right, so what we're going to take a look at next is something called percentiles. And I'm sure you've heard of before, like somebody scored in the 89th percentile or the 92nd percentile. So this isn't the same as a percent. I mean, it's connected to percentages, but say a 95th percentile doesn't mean that you scored a 95%. It's your position compared to everybody else. So percentiles are just a position measure. The word percent means out of 100, so when we're looking at percentiles, we divide the data set into 100 equal groups. Percentiles are pretty much used mostly in educational and health-related fields. What it does is it compares the position of an individual in a group. Percentiles also compare an individual's test score with the national norm. So what I just mentioned, that these are not the same as percentages. A score of 90% just tells you how many problems you got right out of the whole test. It is no indication of your position that WRT means with respect to the rest of the group. What a score of a 90th percentile means, it's your rank. It means you did better. Here's where the percent comes in. You did better than 90% of the rest of the people taking the same test. So again, it's just your position. That means your score is higher than 90% of all the other scores. So please pause this a little bit in order to copy this down if you still need more time. All right, this is just an example of a percentile graph. You don't in any way have to copy this down, but this is just a way to get approximate answers. This is showing the weights of girls by age and their percentile rankings. So notice for the y-axis there, it's the weight in pounds and then the age in years. So somebody who's 11, if we just kind of went straight up here, this is showing us really the percentages here, so they would be in the 82nd percentile. So the graphs may look like relative frequency distributions as well, again, because those show percentages. The cumulative relative frequency is the percent on the y-axis. So a little bit more than the 82nd percentile, or the 80th percentile here, which would be the 82nd percentile. All right, so how do we get the percentile? How do we calculate that from a list of data? There's a formula. So the percentile is the number of values below the x value we're looking at, plus 0.5, divided by the total number of values, and then times 100. Now, even though we say times 100, we don't write it as a percent. We're going to come out with a number like the 56th percentile. But we're first going to get a decimal, which is why we need to multiply it by 100. But you never answer this as a percent. So we could simplify this formula and just say P is equal to C, which is representing the number of values below X, plus 0.5. That's everything up there is C, divided by N times 100. And we're going to round to the nearest integer, because sometimes we will get a decimal, so we just want to round to the nearest integer. All right, so let's take a look at this example going back to test scores. A teacher gives a 20-point test to 10 students. The scores are shown here. We want to find the percentile rank of a score of 12. Well, first we need to put this in order. So let's go ahead and do that. Our lowest score is a 2, then we have a 3, 5, 6, then 8. Then it looks like we have a 10, 12, 15, 18, and 20. All right, so our percentile score, we have to look at all the numbers below 12. We do not include the 12. So we have 6 numbers below 12 plus the 0.5, and we divide that by 10 and then multiply it by 100. So we're going to get 6.5 divided by 10 is 0.65 times 100 would give us 65. So we would just say a score of 12 is in the 65th percentile. So what that means is somebody that got a score of 12 did better than 65% of the class. Let's try the same data here. Let's do a score of 6. So go ahead and pause the video here and go ahead and calculate this. What is the percentile associated with getting a score of 6? Okay, so if we were to look at this, we have 3 scores below 6, so we would take 3 plus the 0.5, divide that by 10 times 100. So that'll give us 3.5 over 10 is 0.35 times 100. This would be the 35th percentile. So we could just answer the 35th percentile. All right, so now we're going to find a data value corresponding to a given percentile. So just pretty much the process in reverse. So again, we always need to remember arrange that our data is arranged in order. So we still need to be given a list of data. The formula here going to be C is equal to N times P over 100. So P is the percentile, and N is the total number of values. Now, the rule here is if C is not a whole number, we round up to the next whole number. Starting at the lowest value, we count over to the number that corresponds to the rounded value. And if C is a whole number, we use the value halfway between this number and the next number that's going to be over. So let me just kind of write those out for you to copy down here. So again, starting at the lowest value, count over to the number that corresponds to the rounded value. So I know this last paragraph is going to sound a little weird, but wait till we do an example. If C is a whole number, use the value halfway between that number that we count over and then the next number. So it's the C and the C plus first. I know that looks a little weird. Values when counting up from the lowest value. So pause the video to copy that down, and we just have one more example to go over today. All right, so let's take a look at what I was just talking about. All right, so here's our test scores again. We want to find the value that corresponds to the 25th percentile. So again, we're looking at C is equal to N times P over 100. So C is going to equal, N is how many numbers we have here. So we have 10 numbers times our percentile, which is 25, divided by 100. So this will give us 250 over 100, which is 2.5. So it says if C is not a whole number, we're going to round up to the nearest whole number, which is 3. So now we count over 3, and that takes us to 5. So 5 corresponds to the 25th percentile. Okay, and example B, we want to find the value that corresponds to the 60th percentile. So if you want to pause this and give this a try, you can, just to find out what C is. So again, we have 10 values times 60 and then divided by 100. So this is going to come out to the sixth number. Now that is a whole, or not really the sixth number, but it just comes out to a whole number of 6. So what we do is we count over 1, 2, 3, 4, 5, 6. So this is our sixth number, but we go halfway in between the sixth number and then the number right after it. So right in between 10 and 12 would be 11. So 11 corresponds to the 60th percentile. So I know that part was a little strange because we found a number that wasn't there. So actually working backwards to figure it out might not always equal the same thing, because if we put an 11 in there, we would actually have 11 numbers and no longer 10. And because other scores could be missing too, it's going to be close enough. If we actually ran this and said if we included the number 11, we would still have 6 numbers below that score of 11. And then it would become the 6 plus the 0.5 divided by 11. And that actually gives us 59%. But that's pretty close to the 60th percentile. So some of these numbers, because our data set is small, could look like that. The 59th, you still did better than 59%, or you still did better than 60%. So that's going to be close enough. So don't expect both ways when you go back to check, as long as it's going to be close enough, that will count for this. So for right now, we're just looking at the process here of using this formula, C equals N times P over 100, to find values that correspond to a given percentile. Now, A works out perfectly. Sometimes it doesn't, and then sometimes we're just close enough. All right, so there's no homework assignment yet for today. I still want to get through the rest of section 3.3. So prepare tonight for the quiz for tomorrow, and please let me know if you have any questions.